In this video we're going to talk a lot about the dot product. I want to start with a little review of unit vectors, but then we'll talk vector operation called dot product. So the first one here, finding the unit vector. Well, remember, unit vector, the first thing we want to do is find the magnitude of the vector we have, because a unit vector should always have a magnitude of 1. So 9 plus 25, so this is the square root of 34. So then we take our original vector and we essentially multiply it by 1 over the square root of 34, or you could think about like I'm dividing each piece by the square root of 34. And the reason we do that is now the magnitude of this new vector is 1. Okay, let's do that with the other one as well. So 2 squared plus 7 squared, so 4 plus 49 is 53. So again, we take our old vector and we multiply it by the scalar 1 over the square root of 53. And there we are. That's it. That's all there is to finding unit vectors. So the dot product. You can see the formula for dot product here. A vector with the components AB and vector with the components CD. The dot product, symbolized by the dot between them, is given by multiplying the x components and the y components and then adding them. So it's a very simple notational, or a very simple calculation. This first one would be 3 times 1 plus 6 times 3. So 3 plus 18, so the dot product is 21. This one would be negative 2 times 6 plus 4 times 9. So negative 12 plus 36, we have a dot product of 24. Now, the dot product has some geometric properties and some geometric benefits that I'm going to kind of start to hint at coming up. But first I wanted to just briefly talk about what happens when you do a dot product with a function or a vector on itself. Now, something that's kind of interesting about the dot product is it does take something with two components and bring back a single number. And again, I'll explain why that has some value to us, or at least show you an example. So let's say that A is dotted with itself. Of course, we'd have, as I defined it before, V is components A and B. So I'd have A squared plus B squared. Well, this is V's magnitude squared. Okay. Remember, magnitude, we use Pythagorean theorem, but of course here we don't have a square root. So when you dot something with itself, you get its magnitude squared. And that has some important properties too. Let's look at the next slide. So, okay, what good is it? Well, I start here with the law of cosines. Remember the law of cosines? This was a way of finding a side length if you knew an angle and two sides on either side of it in a non-right triangle. Okay, so this is the law of cosines. C squared is equal to the other two sides squared, so it starts kind of like Pythagorean theorem and then subtracts 2 times the sides on the cosine of C. So it was a way of finding a side length if you knew an angle between the other two sides. Well, I put this in terms of some vectors here. So you can see I've got vector A, I've got vector B, and this is vector A minus B, or vector, this side length right here. So I've redefined, the magnitude of A minus B is equal to the magnitude of A squared, meaning length, plus the magnitude of B squared, meaning its length, and then minus 2 times the length of A times the length of B. So I've really just rewritten the law of cosines with the magnitudes. Okay? Now I started only working on the left side. We've discovered that magnitude is the same as dotting something with itself, right? Well, this is A dot A minus 2A dot B plus B dot B, okay, if you multiplied it out. Well, A dot A is magnitude squared, and B dot B is magnitude squared. So again, here's what I just did. I'm using what I just showed on the other slide when I did v dot v. I'm saying that the magnitude squared is equal to something dotted with itself, and then I expanded it. And then I used that again. I said, well, a dot a is the magnitude of a squared, and b dot b is the magnitude of b squared. Now let's compare them. Okay, so this was just the left side. I put that right here, and then I rewrote the right side as it originally appeared. Okay, well, look at what's familiar here. This is the same on either side. This is the same on either side. I've got a -2 on both sides. So what must be true is that AB is equal to the magnitude of A times the magnitude of B times the cosine of theta. You say, well, okay, what does that do for us? It allows us to find angles between vectors. And as I said before, a lot of times it's easier to do some geometry with vectors than it is with actual geometry. It's easier to say the side lengths are vectors, and sometimes much easier to do that. So to find the angle, I'd start by dotting, which I did this one already. I had, 3 times 1, and I can do it again. 3 times 1 plus 6 times 3. And then if I want the angle, I would divide both sides by the magnitudes. Okay, so let's think now the magnitude of the first vector. Okay, so 3 squared plus 6 squared. So 9 plus 36 is 45. So of course the magnitude would be the square root of 45. This one, 1 squared plus 3 squared, so we'd have 10. Those would be the magnitudes. So we just have the dot on top and the magnitudes on the bottom, and this would be equal to the cosine of theta. So of course, to get the angle, we would just do the inverse cosine. So we'd have the inverse cosine of 21 over, I guess it would be the square root of 450, whatever that would be. Type that in your calculator, and you'd have the angle between the two vectors. Okay, so there's some nice properties here really relating to law of cosines that we get to use the dot product for. So again, we've got, if I did this one, I'd have -12 plus 36. That would be the dot product. And then the magnitude of the first vector would be 2 squared, so 4 plus 16, so the square root of 20. And the other one, we'd have 36 plus 81, which is 117. Okay? And when we have that, we would just do the inverse cosine. So there's some nice manipulation you could do here. And of course, if you didn't know the dot product, but you knew the magnitudes, not really sure a situation where that would happen, but you could easily find that. But it's really useful for finding angles between vectors and doing some nice geometry when you define the sides of a geometric shape with their vectors. So how would you know using the dot product if two vectors are perpendicular, or many times it's referred to as orthogonal? Well, the cosine of 90 degrees is 0. We know that. So what would need to happen here is we'd need the cosine of theta to be 0, which means that A dot B over the magnitudes would need to be 0. Well, the magnitudes better not be 0. This isn't going to work. The magnitudes can't be 0. So what would need to be true is that A dot B would need to be 0. So it's also an easy way to check whether a geometric shape has a right angle in it. And a really easy way to check if it's a rectangle or square, or not necessarily a square, you could have to use the magnitudes, but at least a rectangle, is to check the dot product between the vectors that form the angle. If the dot product is 0, then we know there's a 90-degree angle.